Here's my magnets. I'm going to place them together. I've hung a thread from the ceiling, and I put this piece of tape on here so that I can stick the magnets on either side of it, and this will allow me to make a homemade compass. If I let it go, it will align itself with the Earth's magnetic field. Now it's oscillating a little bit. I'm just going to help it slow down, and we'll see which way it orients itself. So the Earth's magnetic field is running this way through this room, and if I try and force it to stay over here, it returns back to the orientation of the Earth's magnetic field. And if I turn it completely around, it goes back. Opposite poles attract. Like poles repel. I have a horseshoe magnet on the tabletop, and I've placed it on two pens so that the pens can roll and the magnet can easily move back and forth without the friction between the magnet and the table being a factor. And what I'll do is I'll bring my other magnet, other horseshoe magnet, when the opposite poles face each other, it pulls it together. If I flip my magnet over though, so now that the like poles face each other, it repels. This nail is unmagnetized. I can tell because it doesn't have any magnetic effect on the paper clip. However, iron is easily magnetized. If I take a magnet and stick my nail to it, the magnetic field of the magnet creates a magnet out of the nail, and now I can pick up the paper clip with the nail. And if I remove the magnet, we can see that the nail remains magnetized, but not for a long time. If I whack the nail on the table, the vibration causes the magnetism to go away. So the nail does not maintain its magnetism very well. So this device is a container. It's filled with oil, and in the oil are some magnetic particles, some iron filings, particles that respond to a magnetic field. So I'm just going to shake it up, and then I'm going to place this magnet down the center of it.
And so here's that right-hand rule. If we've got current moving through a wire, this is conventional current, all you do is just point your thumb in the direction of where that current is moving, and then as your fingers curl around, it's going to show you where that magnetic field is. And so right here we've got current going up, so I'm going to put my thumb up, and so then we have the magnetic field that's turning around like that. Say the current's going in the other direction, magnetic field is going to go in the opposite direction.
We have seen what happens when current is flowing through a straight conductor in our previous lecture. Now let us see what happens in a current carrying conductor with a slight twist. Over here we place the conductor in a way so as to resemble a loop. So let us see what happens in a current carrying loop. Over here we find that the conductor has been placed in the shape of a loop and on a plastic board with two holes in it. Now when there is no current flowing, the iron filings are randomly placed. Now what happens as soon as current starts flowing? Observe closely. The moment current starts flowing in the current carrying loop, a magnetic field will be generated, and the pattern of the magnetic field will be given by the iron filings, as you can see. Over here, the iron filings are no longer randomly generated, but they have arranged themselves in a particular pattern around the current carrying loop. So the schematic of the experiment is shown over here. Now over here we have considered a cardboard on which the current carrying conductor is placed in the shape of a loop. Two holes have been considered through which the conductor passes through the cardboard. Now through the placement of the iron filings on both the sides, we are able to find out the pattern of magnetic field. Now how can we find out in which direction the magnetic field lines are pointed? Now we can do either of two things. We can use the right hand thumb rule. So let's see what happens if I use the right hand thumb rule at this end. Now if I consider the pen as the current carrying conductor, I can see that current is moving in the upward direction. So my thumb will be pointing in the direction of current and my fingers will be encircling the direction of the magnetic field lines. So it will be in this direction or in this direction. So as you can see, the field lines are as obtained. Similarly, if I apply the right hand thumb rule at this point, I will find that current is flowing in the downward direction. So I consider my thumb in the downward direction. So now you will notice that my fingers are encircling in this direction. So this direction gives me the direction of the magnetic field lines. As you can see, this is the direction of the magnetic field lines. Take a look at the picture on the screen. Over here you will find that there are many loops over here which have been generated with the help of a single conductor. Now this is a copper wire. Earlier we have studied that how we can twist a copper wire in the shape of a circular loop, and if current flows through this loop, then a certain magnetic field is generated. Now what if in place of a single loop we have multiple loops one after the other? This can be achieved if we continuously twist a conductor in the manner shown. The structure which we obtain is known as a solenoid. So when current flows through the solenoid, a definite magnetic field is generated. So let us see how we can find out the direction of the magnetic field around a solenoid when current flows through it. This simple experiment, in which we use a simple magnetic needle, demonstrates the direction in which magnetic field is pointed around the current carrying solenoid. As you can see, as the needle is placed at different points around the solenoid, the deflection of the needle changes. This indicates that the needle is pointing towards the direction in which the magnetic field lines are pointing. So now let us take a look at another video where we will be able to find out the pattern of the magnetic field lines. In this video, you will find that a solenoid has been considered and the iron filings initially, when there is no current, are randomly placed. Now notice closely what happens when current starts flowing. As you can see at these parts, at the ends of the solenoid, the iron filings come close to one another and they form a definite pattern. You can see that the definite pattern is being pointed out in the video, and the iron filings at each of the holes has formed a definite pattern. And this pattern gives us the pattern in which the magnetic field is present around the current carrying solenoid. So we found out what the pattern of the magnetic field lines are and in which direction they are pointed. So now consider this picture. Let us say I have considered that current is entering from this direction and exiting from that direction. Now let us consider each of these faces separately. When I look at this particular face, I will find that current is flowing in this direction. Now what does this correspond to? If you look at it closely, then this resembles a clockwise rotation. Now if I resemble the clockwise rotation in this manner, I find that it is the letter S. So clearly this is the south pole, because if you recall from our previous discussion on a circular loop, when we have clockwise rotation of current, it implies the south pole. Similarly, if we consider the other face, we will find that current is leaving the face in this manner. So if I have to look at that face from this side, I will find that current is moving in the anti-clockwise direction. Now, what had we studied about anti-clockwise direction of current in a circular loop? We had found that if we consider the letter N and place two arrows at both ends, this indicates anti-clockwise direction. So this is the north pole of the solenoid. And as you can clearly see from the field lines, the magnetic field lines are leaving the north pole, traveling all the way outside the solenoid and entering at the south pole. And inside the solenoid, they are traveling from south to north. So what does a solenoid behave as? Doesn't this behavior of magnetic field lines seem familiar to you? That is right. This solenoid has field line configuration that is very similar to that of a bar magnet. So over here we have a bar magnet, and over here we have a solenoid. So as you can see, the field lines, that is the magnetic field lines around a solenoid, have a similar direction and orientation as the magnetic field lines of the bar magnet, provided the north and south of the solenoid as well as the bar magnet are facing the same direction. So we have found out that when current is flowing through a solenoid, and if we look at the solenoid from the top, then this is the south pole because current is in the clockwise direction, and this is the north pole because current is in the anti-clockwise direction. So this is how a current carrying solenoid resembles a bar magnet.
What exactly is a magnet? What makes some materials, like iron and neodymium, magnetic, while other materials, like copper, tin, and plastic, are not? To answer that question, we'll have to look through a microscope. Scientists now believe that all magnetic fields are created by those all too familiar charges from your days of chemistry: electrons. All moving electrons, whether they're zipping down a power cord or orbiting around an atomic nucleus, generate a tiny magnetic field. Those fields may be small, but they add up, with the potential to create fields large enough to encompass the entire Earth. When we look at this piece of iron under a microscope, we see what appear to be tiny cells. These cells are called domains. In metals like iron, quantum mechanical effects cause the electrons in these domains to share the direction of their magnetic field with other electrons. As a result, each domain has an individual magnetic field. In a non-magnetic material, these fields point in random directions, like toothpicks scattered on a table. The thousands of domains pointing one way cancel out thousands pointing the other. The result is a non-magnetic piece of iron. When we look at this magnet, however, we see that the domains are preferentially aligned in one direction. What has happened is that as this magnet was made, its domains were twisted by an outside force, such as another magnetic field, so that most of them point in the same direction. Instead of canceling out, all these magnetic fields add up, creating a much stronger magnetic field that surrounds the entire piece of iron. And we get a magnet.
I'm going to take my magnets and align them so that both south poles are facing the same direction, and I'm going to see how close I need to come to the paper clip before I draw it over. So 1, 2, 3, 4, 5, 6 lines on my line paper away. Now I'm going to align a north and a south pole, and I'll do it again, and this time I get much closer before only 3 lines away before the paper clip is drawn to the magnets, indicating that in this orientation the magnetic field is not as strong. That's because in this orientation the magnetic domains are canceling one another, whereas in this orientation they help to reinforce one another, making a strong magnetic field. This is an electromagnet. These 2 wires here are connected to a coil of wire that runs in a circle many times around this iron core. Right now, the magnetic domains of this iron core are randomly oriented. So this plate of steel does not stick. You can see that the iron core is not magnetized. However, if I connect this battery, I'm going to run a current through the wire that is looped many times around the iron core. The magnetic field caused by the current is going to help to align the domains inside the iron core, causing it to become magnetic. And I get my electromagnet, which can be very strong. I'll turn my electromagnet on. Now I can pick things up, and when I turn the electromagnet off,